Let's begin our study of open system problems by looking at the continuity equations. And we'll do that by solving 6 different continuity problems. So let's start by looking at the conditions under which we'll apply the continuity equations. These apply to open systems that operate at steady state conditions, that have a single inlet and outlet, and have one-dimensional flow, which we'll assume for all open system problems. One-dimensional flow simply means that the properties of the fluid are identical over the entire cross-sectional area perpendicular to the flow. So let's begin with looking at mass flow rates. The first continuity equation says that the mass flow rate at the inlet is equal to the mass flow rate at the exit, or we'll just call it the mass flow rate since they're the same thing. And we'll use a variable value, a small m, and we'll call it m dot. I cannot place a dot over an m, so I've used a prime here, but we'll read that as m dot. The volumetric flow rate for one-dimensional flow can be said to be this, that the volumetric flow rate is just the area times the velocity, but it's also the mass flow rate times the specific volume. And the remaining continuity equations are just derived from the first two. So they're just rearrangements of the information we've already seen. We can say that the mass flow rate is the volumetric flow rate divided by the specific volume. But since the volumetric flow rate is the area times the velocity, then the mass flow rate can all be written as area times velocity divided by specific volume. Now the inverse of specific volume is density, so the mass flow rate can also be written as just rho AV. We can also write an inlet-outlet ratio, and again this is just derived from the previous expressions. We can say that the area times the velocity divided by the specific volume at the inlet is equal to the area times the velocity divided by the specific volume at the exit. Let's solve our first problem with open systems. A laser Doppler velocimeter measures a velocity of 8 meters per second as water flows in an open channel. The channel has a rectangular cross-section area of 0.5 meters by 0.2 meters in the flow direction. If the water density is a constant 998 kilograms per cubic meter, determine the mass flow rate in kilograms per second. Well, we have a schematic of this. We've got a rectangular channel whose width is 0.5 meters and whose depth is 0.2 meters. The water flow is perpendicular to this cross-section. And what we're given is the density of the water and its velocity, as well as the channel dimensions. So the area of the channel that the water sits in is 0.2 meters by 0.5 meters, or 0.1 square meters. We're going to model this as an open system operating at steady state, and we want to find the mass flow rate in kilograms per second. Let's solve this problem. We'll use one of the simplest equations, one that's you may already be familiar with, is the mass flow rate is simply rho AV. It's the density of the liquid times the cross-sectional area times the velocity. We have all of these values. We know the density, we know the cross-sectional area, and we know the velocity. So we calculate that the mass flow rate is 798.4 kilograms per second.